So this is the second of our medallion lectures, supported by the IMS. As I mentioned before, the IMS names a number of excellent probabilists and statisticians to give special talks at various meetings throughout the year. We have 2 medallion lecturers here. The second medallion lecturer is Krzysztof Burdzy, someone I've known a long time. After doing his undergraduate and master's work in Poland, he got his PhD at University of California, Berkeley. Did postdoctoral work at San Diego, in a postdoctoral position, and then took a position at University of Washington in Seattle, where he has been since, and he currently holds the title of professor. Among his honors are the Rollo Davidson Prize, and he's a fellow of the IMS and the AMS. I'd also like to say, since I'm here, I get to say some personal things. As I say, I've known Chris for a long time and admired his work for a long time. In terms of with me, a couple of things I do remember very early in my life, in my career. He's the one who actually probably first convinced me that conformal invariance of Brownian motion was a very important thing. I was a discrete person before then, and he changed me, at least partially. Secondly, in terms of achievements that we were talking in a conference 1995, SPA, and worrying about the price of journals, and that's where over breakfast in Florida we actually made a decision to start a new journal, which is now a well-established, the Electronic Journal of Probability. Rene Carmona also joined our team at that time. And happy to say that this is now one of the most successful electronic-only journals in the mathematics community. That's also due to a lot of hard work of people after us, but I don't get to mention their name today. And Chris has been involved in a number of other things in the promoting of mathematics on the web. I won't list them all, but I will say that he got a much-deserved Carver Medal from the IMS a couple of years ago in honor of his service in those things. Today Chris will be speaking on the Archimedes principle for a ball in Knudsen gas, but before you start clapping, we have to give a medallion.
Thank you very much. I wonder if you've heard the sound. This was the sound of gold. Okay, so first of all, I'm very happy to be here. It's a great honor and privilege to be at the conference and to be invited to talk, and it's a great honor to be awarded the medallion by the Institute of Mathematical Statistics. So I appreciate that very much. So today I will talk about the Archimedes principle, and I will start a little bit with a motivation. So actually, I will not talk about this project. I will have just one slide on this old project, and I will try to explain how this motivated the current work. The current work is an ongoing work. This is already published. So this was joint work with Zhenjin Chen and Shumik Pal. And at that time, since we were working on a particular version of Archimedes' principle, we searched the literature, the mathematical literature on Archimedes' principle, and we could not find anything. So I and my co-authors repeated the search this time. We are currently working on a different project that I'm going to report on. And once again, it appears that there's absolutely nothing in the math literature on Archimedes' principle, well, except for one paper over here. I will return to this point in a few slides. I have a theory, a good theory, why there is absolutely nothing in the math literature on Archimedes' principle. So let me say what we proved in that paper. So we proved Archimedes' principle, separation of oil and water, right? Oil and water, and also the disappearance of bubbles. But in that project, okay, so obviously we had to have some idealized model, right, for liquid and so on. And in our model, we had balls that were moving according to Brownian motions. These were independent Brownian motions, except that when the molecules or balls or whatever you want to call them, when they collided, they reflected. So they were reflected Brownian motions. They reflected from the walls of the container and from each other. But the driving Brownian motions were independent. In that project, we fixed the number of molecules, and the theorems were asymptotic. Asymptotic in the sense that the gravitational acceleration, that g, was going to infinity. Okay, so I have to say that I had a lot of fun with that project, and I am very proud of those results. But frankly speaking, this is not what like a typical physics project would look like. But because first of all, we already assumed that the molecules were moving like Brownian motions, right? So in some sense, we already skipped some, one step, and we went like one level higher. Now, second, in reality, the number of molecules and the gravitation don't go anywhere. They are both constant. But it feels like, it's our sort of, this is how we think about the world, right? That the gravitational constant is fixed. And we think about the number of molecules as being huge, so in some sense it goes to infinity. So in some sense, those asymptotics were sort of wrong asymptotics. So I will try to, so the current project tries to remedy this. And in the current project, we do not start with Brownian motions. We start with sort of classically moving particles or molecules. And we will, in the current project, the gravitation is constant, and the number of molecules goes to infinity. So basically, it's a different model, and in some sense, I hope it looks a little bit better. Okay. So first of all, well, let's recall the Archimedes principle. The upward buoyant force that is exerted on a body immersed in a fluid is equal to the weight of the fluid that the body displaces. Now, fluids come in two versions, two types. There are liquids and gases, and the consequences of Archimedes' principle are different. In both cases, you see Titanic had no choice but either to float on the surface or go to the bottom. All objects that float in between, like fish or submarines, actually have to use active control. An inanimate object either will sink to the bottom or float to the surface. And it's different with gases. A helium balloon will go up, 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 and at a certain point, it will just stop. It will just float at a certain level. And the reason is this. Today I will talk about gases, so I will have much more to say about this kind of model. But the difference is that, the reason why there is a difference between liquids and gases is because liquids are incompressible. So the pressure is just a linear function of the depth. And in gases, the pressure is an exponential function of height. So this is, that's the major difference between the two models and, consequences of Archimedes' principle. Okay, so I will talk about a gas, and I'm not sure about the terminology. I've seen both ideal gas terminology and Knudsen gas terminology. So it seems to me that I think maybe on the math side, ideal gas is more popular. It means gas in which the molecules do not interact at all. They never collide. And well, actually, so I checked in the air. The average flight between two collisions is about on the order of 100 to 1,000 diameters of the molecule. But I don't know if it's infinity, but this is already sizable. Now, Knudsen worked on gases that were really diluted in the sense that if you have a macroscopic container, then basically there will be no collisions during the flight from one wall of the container to another wall of the container. So for all practical purposes, the molecules do not collide at all. Okay, so let me remind you that there is no mathematical literature on Archimedes' principle. So here's my theory why. Suppose that you already already know the concept of pressure and you have some theory that tells you what pressure is. Once you have pressure, then there's basically nothing else that you have to do because the divergence theorem will give you Archimedes' principle. You just integrate that vector, right, the vector of forces, right? The pressure translates into force on the boundary, and assuming this is smooth boundary, you just integrate, and what you will get is the right answer. And that's it. So there is no point of publishing an article on Archimedes' principle, of course, assuming that you already have a theory of pressure. But, okay, so the problem with this statement as is, at least that's how I see it, is that this, at least implicitly, assumes that this body, whatever it is that is supposed to float, is not moving. So it's like we are holding it, right? And then you do the integration and all that. Well, but what if you release the body and it can move? And then all of a sudden the problem does not seem to be trivial to me because you can model the problem in different ways. And so suppose that you want to have a continuous model for the fluid. Okay, so now we are talking nonlinear PDEs, and that, frankly speaking, I don't know that field, but I sort of doubt that you could prove Archimedes' principle from sort of nonlinear PDE side. I don't think that they are there yet, but even if you can do it, it doesn't matter. This is a highly non-trivial theory, right? So all of a sudden, Archimedes' principle is not trivial. The second thing that you could do is the following. You could say that the macroscopic object that is supposed to float moves at a scale that allows the gas to equilibrate extremely fast, which means that if that object is low or high or moving, the gas is always in the equilibrium state, right? And under some assumptions, this is a reasonable assumption. Well, the problem with that is that, if you assume that, so if that object will be below where it should be, there will be a force pushing it up. If it's above where it should be, there will be force pushing it down, and the object will start actually oscillating. It will not be sitting there. It will be oscillating. And based on what I know about both physics and mathematics, this is not going to happen. Okay, so what's wrong with that? Well, what's wrong with that is that the kinetic energy of the object will be transformed into the heat energy. Okay, and so we could add that to the model, but once again, this is all of a sudden becomes non-trivial because there is some rate of transfer of kinetic energy into heat energy and so on. So, well, my point is that somehow for a moving object, Archimedes' principle does not look to me that simple anymore. And by the way, concerning the transfer of kinetic energy to the heat energy, this is sort of implicit in our project. So we do not state it that way, but our model has this in an implicit way. Okay, a few words about, I just stated that the pressure in gas is the exponential function of altitude, of height. Okay, so that's the formula. The pressure is some kind of exponential, so there's probably some normalizing constant in front. And, if you want to do it, well, this is not even hand-waving. The point is that if you make certain assumptions, then the formula is immediate. Okay, so you have to assume, first of all, that the pressure is proportional to the weight, and, there's this PV over T formula. If you assume that, then you can derive the formula for the exponential, the exponential form of of pressure as a function of height. So at least this is a justification, why it sort of makes sense. But we will be, in our project, we are dealing with the ideal gas, or Knudsen gas. And you see, in the previous picture, well, actually, I have this picture here. You see, in this picture, we can think about layers of gas pressing on other layers of gas. Just physically, I'm just squeeze something and it's pressing on the next layer and so on. And therefore, the layers at the very bottom, that contain the same volume, right? Or the same mass, not the volume. The same mass of gas, are, compressed. Well, with the Knudsen gas, particles just don't collide with other particles. So this is a trajectory of a single, molecule. And one could probably think about, layers of stationary distribution pressing on layers of stationary distribution, but this becomes very abstract. There are no physical layers of gas pressing on physical layers of gas, right? So you have to go to some abstract space to even think about this. Okay, so first, just a general remark. How we approach the problem. So we approach the problem by starting with a container. The container is semi-infinite in the following sense. The base is some smooth domain, bounded, and this is, it's the product with a half-line. So there is no top. This container has no top. It has the bottom. Although, frankly speaking, the fact that this container has no top is irrelevant because we will give only a finite energy to the system. Once you have the finite energy, the balls, and the macroscopic ball and the molecules cannot just go too far. So I could have as well put some kind of top or lid on the container. And it turns out that there is an explicit formula for the invariant measure. And you might have noticed that I put question marks here. This refers to explicit, and then I wasn't sure whether I should say n or the invariant measure. So I will comment on both of these parenthetical remarks later. Okay, so that's the theorem. It's forthcoming. It's a forthcoming project, or forthcoming theorem. The project is already going on. And I call it a forthcoming theorem in the following sense. I believe that we have already all technical mathematical ingredients. We are not finished with, this is a computational project. There are lots of computations. We are not finished yet. I believe that we are like epsilon away from the result. But, honestly, we are not there yet. So what I'm going to do is I'm going to make a number of general remarks, and then I will also talk about some specific technical parts of the project that I think that actually can be presented in a reasonably clear way. I will not present any formulas because I don't think that they're interesting because, unless you spend some time, doing some calculations, they are basically meaningless. I don't. In our project, there is no pressure. But since in this model there is no force because there are instantaneous elastic collisions, then you can either say that whatever the force is, it's infinite or it doesn't exist. Then there's a substitute for that. Namely, every collision is an exchange of momentum or change in momentum. And then instead of pressure in terms of force, you can basically study the change of momentum. So that's the way to deal with this. Okay.
One more question. So it's 3D case.
No. Our calculations work in all dimensions, and I will talk about that. But we are really interested in 3 dimensions, but it's basically the same formulas in all dimensions. So I have to apologize. I mean, it was a good question. You know what? I stated some theorems later with a D and a number of dimensions, well, at least two or greater, and some of my formulas have 3, you know, and I will try to comment, yeah.
Do you show it's a balloon in Knudsen gas?
Yes. Yes. By the way, you know, Knudsen gas, the way I presented it, is like it's almost non-existent. Well, actually, ideal gas can be very heavy, because the point is not how heavy the particles are or how many, but how small they are. So the point is that you can have extremely heavy gas with extremely large number of particles or molecules, but if their radii are small, then still they will not see each other.
So basically, the heat independent. Okay? They're just
Yeah. So, okay. Independent here is that in some sense it's crucial. The molecules will not collide, but they all collide with a macroscopic object. So they are not independent. They're independent as long as they're sort of flying away, but once they start interacting with a moving object, then that's sort of where the dependence comes from. Okay, so a few words about what this theorem means. So first of all, this theorem is an asymptotic theorem. In this theorem, the number of molecules goes to infinity. But we keep the total energy constant, the mass of the macroscopic ball constant, the diameter of the macroscopic ball constant, the total mass of gas constant. So if the number of molecules goes to infinity, it means that the mass of a single molecule goes to 0. It's the product of the two is constant because the total mass of gas is fixed. Now, the number, I mean, this has to be an asymptotic result because if you have just one microscopic ball and 7 molecules, then it's hard to say what even Archimedes principle means. So n has to go to infinity to get something meaningful. The second thing is about temperature. You see, once again, if you have even 1 million molecules or 10 to the power 100 molecules, and the temperature is very low, very, very low, then everything is sitting on the floor, right, at the bottom. The macroscopic ball and all the molecules are sitting there, and once again, it's very hard to say what Archimedes principle means. So there has to be some temperature. So I don't know whether we will be able to state exactly what temperature we need, but the temperature cannot be low. It has to sort of be at least, so that you have actually some gas where that object can be floating. Now, the next thing that I wanted to say is about the container is large. Okay, so let me say a few words about this. Before the size of the container. Archimedes' principle can be interpreted in such a way that it's basically a tautological statement. Completely tautological. Because imagine some kind of mechanical system in which nothing is moving. You see, if there's no wind and no draft, we humans think that the air is just not moving. Molecules are moving. Well, nowadays we know, but it just does not appear that anything is moving. So we can think about, some kind of region in the space, and there's something inside it. Well, that something is air. So there's air here, and nothing is moving. So then I take that air and replace it with a helium balloon. And I say now that the weight is the same. What is the weight? Weight is the force, right? So there's something in the system, and there's some force, and then I replace this object with some other object, but I do not change the force. Well, I mean, then it's obvious that nothing is going to move in that system because I replaced one part with another part, and the forces are exactly the same as they used to be, right? So my point is that in this interpretation of Archimedes' principle is sort of a tautological statement. So what is this theorem about? So about two things. So first of all, we get a sequence of models. It's not one model. For every every number of molecules, we have a different model. And in every model, under the stationary distribution, the macroscopic object has a certain distribution, right? So the height. And the point is when n goes to infinity, these random variables that represent the height, will go to a constant in distribution. And the second thing is we have to identify the place. So basically, well, we have to have somehow a meaningful way of saying, well, that's Archimedes' principle. And now the question is how to express that, because, once you accept Archimedes' principle, as I said, it's sort of tautological. You may say, okay, so you have this exponential distribution for gas, you just find the right spot and you place your helium balloon there. Well, that's one way to do it, but I will show you a sort of a different way of thinking about this, because actually in our project, we fixed the energy. So we did not say, well, that the distribution of gas is fixed. We said the energy is fixed, and then the things become a little bit more interesting. At least they become more interesting to me. This is a theorem that I have learned just very recently, and it's a striking theorem, and I don't know how I could have lived, all my life without knowing it. It's an old theorem. It's a virial theorem by Clausius, and it says the average kinetic energy is equal to 1/2 of the average potential energy. So this has nothing. Well, I guess it has something to do with randomness, but basically you have a mechanical system. Think about a sort of dynamical system. And so apparently astrophysicists are interested in that because you can think about a star. Forget that thermonuclear energy, whatever it is, or nuclear energy in the star. Think only about kinetic energy and gravitation, right? So every two particles, every two molecules in a star exert, gravitational force on each other, right? And they also, move. So there's some kinetic energy, some potential energy, and it's just amazing that for a huge number of systems, this is 1/2. And so, first of all, it's amazing that this is some kind of universal number, and it's also amazing that it's so simple, and so it's a wonderful theorem. But in our case, it's a different constant. And by the way, since you asked this question, this is not 3, this is the dimension. Yeah, so it's the dimension, but I just stated it for the 3-dimensional space. So it is not always 1/2, because actually, somehow the original systems were such that it was always 1/2, but, this is already an old theorem, and there's some whole theory, and you can get other fractions, but typically they are very nice. So in our case, this is 2/d. It's a very nice fraction.
Is the reason why you switched kinetic and potential energies as compared to classical?
Is there a reason why what switched potential to kinetic, or?
1870, it's like average kinetic energy is proportional.
Oh, and why I stated it in the terms of potential? I wasn't thinking about this because in our project. Okay. And by the way, I wonder if you noticed, but in that statement, of that theorem, I'm talking only about molecules because that macroscopic ball has to be sort of set aside because it has negligible kinetic energy, so it would not fit into any nice theorem. Okay. Okay, the title of this slide is, I wanted to make it interesting, okay, saying that the Archimedes principle is false, is going a little bit too far, but we just have to think for a moment. I just want to explain something. You see, on the previous slide, I said that we prove Archimedes principle for a large container. So what's wrong with a small container? There's nothing wrong, but you just have to think a little bit. Suppose that you have a small container filled with gas, then you do some calculations, and you say, okay, if I want to put, I don't know, a balloon or something in that container, and I want that balloon to float, okay? So what you do is you take your balloon and you insert it exactly at the place where it should float. Well, it depends what you mean by doing calculations and so on. The point is that if that balloon goes into the container, it will displace some gas. And that gas has to redistribute itself within, the container or the remaining space in the container. And the way the Archimedes principle is stated, in a popular literature, it's in a very simple way. Basically, there's some gas that was displaced, right? But in this case, this will be imaginary gas. Namely, there's a new distribution of gas in the container, and now you have to imagine that this distribution is sort of prolonged or it's like analytic continuation of a function, right? Inside that ball. And this is imaginary gas that is missing. I hope that it sort of makes sense. There are two distributions. Before you insert that floating object and after, and it's the distribution that after that matters. So the original statement of Archimedes' principle might be misleading if you didn't think about this. And, well, the reason why I'm talking about this is because the formulas obviously become more complicated. Because now, if we think about a balloon and the whole atmosphere, then obviously if you release a balloon that is not going to change anything about the atmosphere, the distribution of gas in the atmosphere. So this is basically fixed, right? But in a small container, this is not fixed. And small, well, from our point of view, all containers are small because we are working with probability distributions, and therefore we are working with finite space, right? We can think about, the atmosphere around the Earth as infinite. But in our cases, to actually do calculations, we do not work with an infinite measure. We work with a finite measure, normalizable measure, probability measure. Now, let me say a word about what's in the literature. Well, what I know about literature. So, in 1999, Lieb published an article. This was probably, I don't know, maybe some birthday conference or something. He published an article with a number of what he called like open problems in statistical mechanics or statistical physics. And one of them was about a piston. And what happened later, according to what I've seen, is that a number of our articles appeared. So probably like there are 20 already articles on MathSciNet, so it's on the mathematical side. But the funny thing happened is that they were inspired by Lieb, but the models that actually are sort of solved or studied in the literature are not the original model. So I will not talk about the original model. What I'm going to show you is the models that are closer to what we are doing. So as I said, there are probably like 20 papers that cite Lieb, and so I apologize to all authors who are not cited here. I will tell you about just one model. So it looks like, so first of all, this is the piston, macroscopic meaning, non-trivial mass, microscopic mass. And there's gas on one side and gas on the other side. Now, you may think that this is, there are some gaps here. No, there are no gaps. I just wanted to show that the piston actually can move left and right. Okay? So gaps, but gas cannot go from left to right. There's one volume of gas trapped on one side, one volume of gas trapped on the other side. And then you can start asking questions. So this is obviously a similar model. The differences are that there is no gravitation here. Second, that instead of one body of gas, there are two bodies of gas. And the third one, I would like to point out that this piston is a certain idealization which ignores a certain effect. You see, in this model, angular momentum is completely ignored. Because when molecules hit, say, over here, that should give some energy into angular momentum. And basically, this does not happen. The piston just moves like that. So the reason why our theorem is about a floating ball is because I want to be a little bit more honest. If you have a ball, and if it's perfectly smooth, so no friction, well, whatever, that's an assumption, then actually there won't be any angular momentum energy. And therefore, it is a little bit more honest to ignore it. So that's the difference. Okay, so as I said, I will try to present a few things on the technical side that I think that can be presented. So first, the invariant measure. So this invariant measure is known as Liouville measure. Well, some people call it Liouville measure. Some people call it microcanonical ensemble. And I don't know, maybe if this is the first time you see the formula, this may look nasty, but actually it's an extremely simple formula. So first let me say why I put this part of the formula in red, because this is the only part that I consider interesting. And the rest is sort of, once you understand what it is, it's rather simple. So, well, first of all, there's a constant. Depending, the formula is actually true in the whole Euclidean space. So it could be considered to be an infinite measure, or you can truncate it to a container, and then it can be normalized. So this C is either completely arbitrary, or if you want to normalize it, then it would have to be a specific, partition function or whatever you want to call it. E is the total energy. This is the potential energy. Mi is the mass of any ball. Yi is the height. G is gravitation. So basically, this sum is the potential energy. So this is the total energy minus the potential energy of all objects. You raise it to this power, and then you multiply. Okay, so this looks awful, but this is actually very simple. Imagine that all objects, no matter what the diameter, they have the same mass. Write all the velocity vectors as one huge vector, so it will have n times d coordinates. And this vector has the uniform distribution on the sphere. Okay, now if the masses, so what this means is that all velocities have the same distribution, and actually it's more or less normal. But since the masses are not equal, you have to do some normalization, and then what it means is that all objects will have not the same kind of velocity, but they will have the same kind of kinetic energy. So basically, it's the same amount of kinetic energy per object. Now, so there's something amazing about this microcanonical ensemble from the point of mathematician. It looks like every math physicist and probably, every physicist knows this, and this is, probably considered absolutely obvious. But so far, I could not find a proof. Now, I'm not saying that the proof doesn't exist. It's just apparently there is no custom of proving basic theorems in physics or math physics. I assume it was proved, a long time ago, and now everybody knows. So imagine that you cannot find a proof of Ito formula or the central limit theorem because it has been proved a long time ago, and there is no point of reproving it in modern textbooks. So if anybody here knows of a contemporary book, textbook or monograph where this can be found, that would be, I would be very much interested. And so what we decided to do, I invited Robin Graham, who is one of the co-authors, to help us. I'm not good with differential geometry, so he's a differential geometer, and he says the proof is at the level of graduate course in differential geometry. Well, fine, but why it's missing from textbooks, I don't know. If it's so simple. And the second thing that we need, for our project is the invariance of this measure not only under the time flow, but also under collisions. So who knows, maybe, I think that it is sort of implicit in physics, but once again, even if I couldn't find the first invariance, it's even more hopeless to find the second invariance in the physics literature. If they didn't bother to prove the first one, then probably I cannot find the second one. So these are not very hard, but I'm just saying that we have to do that. Now, so in some sense, the main technical ingredient, or one of the main ingredients on our side, the mathematical side, is to represent the phase space. You see, you remember those question marks? I said, that there's an explicit formula for the stationary or for the invariant measure. Well, this is definitely explicit. This is as explicit as it can be, but there's something missing here. Namely, what is missing is the indicator. Because this formula applies only if we have this container, right? Applies only when the balls are in the container and they are disjoint. And whether you call it explicit or not, from my perspective, this is not very explicit because you want to do some calculations. All of a sudden, you have this rather unpleasant indicator. So What is here in this picture, what it represents is basically a representation of the volume in the phase space, because you want to do integration, so you have to know how to integrate. So the way you do it is you put a Poisson process. I wonder if you've noticed that these dots are not small circles. These are actually filled circles. These are supposed to be points. So intuitively, they represent the distribution of gas. But on the mathematical side, the interpretation is slightly different, because the little circles represented moving molecules, and these points are not moving. These points represent the volume of the phase space. So if you arrange all these points into one vector, then this is a uniform sample from the phase space. So that's the idea. This gives you a representation of that bounded volume in the phase space. And then it's a little bit, so then the next step is to actually put a ball there, macroscopic ball, and then things become a little bit more complicated, but well, I believe that doable in the sense that we have some formulas, and I believe that, that they are correct. So you can deal with this. And well, what I mean by this is that I believe that we have formulas that we can work with and get the result. Now, in the second hour of my talk, I will address the question of that was in the second parenthesis. I said I wasn't sure whether the invariant measure is unique or not, right? I said an invariant measure or the invariant measure. And okay, so this picture basically is supposed to remind you that there are some invariant measures that are sort of uninteresting, because what you can take, right? We are talking about a whole bunch of balls. There's a macroscopic ball, and there are many small molecules, also balls. If you arrange them in columns, and if you give initial velocities to all of them that are vertical, then they will all always, forever, they will stay on those vertical columns. And that's an invariant, measure, and that's not very interesting. Okay, so what do we do? Okay, so I'm going to introduce random reflections. This is a cheap trick, because, this is very well known that if you have either for certain PDEs or for certain dynamical systems, if they are not nice in some sense, if there are singularities or whatever, if you add noise, that smooths things out and makes things perfect. So, simply the idea of adding noise is not very innovative. But there are two, I would say, intellectual challenges in this case. I want to add noise that, first of all, is realistic, more or less, from the physical point of view. And second, I don't want to destroy the invariance property of that measure. You see, I'm working with an invariant measure, and I want that invariant measure to stay invariant. I don't want a new measure, because I don't know how to work with other measures. So Knudsen appears for the second time. It's the same Knudsen who had a different idea. It was an idea about how gas molecules reflect from the walls. And this picture should basically suggest that the reflection distribution is such that it's proportional to the cosine alpha, right? So from the normal. So basically the highest probability, right, of the most likely reflection is vertical, and then the density goes down to 0 when it is when the angle becomes pi over 2. Now, normally I talk about Lambertian reflections, because actually Lambert was, it's not invented. I mean, for this distribution, inventing it is probably not a good word, but sort of realize that it's relevant, physically relevant. So Lambert was much earlier, but normally I say Lambertian, but in this case, probably Knudsen makes more sense. He was much later, but he actually studied gas and reflections of gas molecules. Now, why Lambertian? I will try to explain why Lambertian, but first let me tell you what Lambertian means. Moon is Lambertian, I claim, and oranges are not. But actually both statements are fake, and I will explain in just a second in what sense. A ball is Lambertian when it appears to have constant brightness everywhere. Okay, so first of all, Moon has all kinds of mountains and craters and so on. But look at the center and go from the center to the edge along this radius. At least according to me, it's the same brightness. So that's what it means that it's Lambertian, right? Because the surface curves, but you have this impression of constant brightness from here to here. And obviously, it's not the same. It's not the same here. So both illustrations, this is a good illustration, but both pictures are fake illustrations for the following reason. By the way, this is not my picture either of the moon, or I just stole both pictures from the web. In this case, it is obvious that the photographer put lighting in such a way as to emphasize the three-dimensionality of orange. And my opinion is that orange is actually Lambertian, that the properties of the surface of an orange peel, I think that it's actually Lambertian. So this effect, this is a fake effect due to lighting. And, okay, so who put the wrong light on the moon? You see, the sun. You see, because the Lambertian effect to be meaningful, or the Lambertian effect requires that every part of the surface gets the same amount of light. And obviously, there's, sun shines only from one side. So I don't know why we get this effect, but there's some fun effect. I don't see that. You see what I mean, right? Every part of the surface should get the same amount of light, and obviously, if the surface is curved and gets light just from one point, basically from the sun, it shouldn't be the case. Well, anyhow, but at least you should know what Lambertian means. Okay, now, so why is it relevant? Okay, so there are two theorems in the literature. So Ferris was first, and then I had a paper with Omer Angel and Scott Sheffield, and we have theorems, and none of them says what you see here, but what I state here is pretty much an obvious and easy corollary of what we proved. Namely, that if the reflection distribution does not depend on the angle and location of incidence, then it has to be Lambertian. So this is some kind of mathematical justification of Lambertian. In this room, I wonder if you can see this, but if you look somewhere here at the top, at least I see on this side, and probably you can see on both sides, that the lamps are reflected, right? Do you see some reflections of the, because there are lamps, in the ceiling, and anybody can see the reflections a little bit? Okay. So what this means is that this surface works a little bit in the classical case, specular reflection when the angle of reflection is equal to the angle of incidence. But if you look at the panels, right, those panels, they appear to me just gray in this lighting, and you do not see any reflection of any object. So what this means is that from our perspective, when we look at those, just move your head a little bit, and you see more or less the same, right? So what it means is that even if light rays are really small, right? So if you move your head a little bit, it means that that surface has to be sending light rays in random directions, and basically in lots of them, right? Because you see more or less the same if you move your head one way or the other. You can't tell the difference. And obviously, we think that a small, say, crystal, cannot send light in all directions, but that's what it appears, that every point on the surface sends light in every single direction. So, in that paper with Omer Angel and Scott Sheffield, we proved that Lambertian surfaces exist. This is sort of ridiculous because, Lambert discovered this a few hundred years ago, but think about this. Physicists obviously know that Brownian motion exists, right? And we mathematicians have to prove that Brownian motion exists, right? So this is the same idea, Physicists simply know that Lambertian surfaces exist, and, well, we try to prove that. So what does it mean? Well, we proved something. Namely, the idea is the following. We proved that there exists a sequence of surfaces such that they appear to be smoother and smoother. So, the roughness is in a thinner and thinner layer. We assume that the reflections are actually classical specular. So think about like small crystals. So no quantum effects, right? No quantum theory. We are at the sort of classical physics level. In that surface, the blue here, the blue line segments represent crystals that they reflect. And what we proved is that if you place those crystals in an appropriate way, and if you look at the reflections, okay, so if you look at this microscopic scale, what you will see is deterministic reflections. If a light ray comes here, reflects once, twice, and goes out, and that's it. This is non-random. But if you are farther and farther away, you will have that impression of randomness, and this will be Lambertian. So in the appropriate sense, once you pass to the limit, you get Lambertian reflection. So it means that basically you will have that impression that every point sends light according to that cosine law. And, if you wonder, so how this was achieved. So first of all, these lines do not mean anything. I'm just saying where we place those crystals. So there's no reflecting surface here or here. These are just placeholders. So I place some reflecting crystals here and here and here, and this is a fractal construction. So there are, smaller and smaller pieces and so on. And that was the construction of a sequence of surfaces that become closer and closer to the Lambertian ideal. By the way, reflections don't have to be Lambertian. And these are examples. So first of all, bicycle. Well, it doesn't have a bicycle. There are also retro reflectors on cars, right? Even if you do not switch lights. There's this whatever plastic thing in the back. And, that's, reflective paint. I wonder if you've noticed that, you might have seen very old street signs or traffic signs. Very old ones, are not that well visible, and all the modern ones are very well visible, and this is because of the reflective paint. This paint basically reflects the light rays in your direction, right? They come from your car, and the light goes back to you. So it means that, people actually can create non-Lambertian surfaces, and, it's not true that all surfaces have to be Lambertian. That's actually a practical example. So let me remind you why I'm talking about this. Well, the reason why I'm talking about this is that if we add that reflection, and I have just tried to argue that it's sort of the good kind of reflection because it is physically somehow justified, well, and this reflection actually will conserve or preserve that invariant measure. And then we have the unique stationary probability because then, because of that noise, extra noise, one can do basically a coupling argument, and we will have just one stationary measure. So this is why we needed that extra noise. And well, I guess everybody wants to go and have lunch and have free afternoon. So thank you very much for your attention.
We had questions during the talk, and I think we have some restrictions how long we stay here. So I'm going to ask people if they'd like to discuss this interesting talk more with Chris, to come up and just talk to him personally. And let's thank him again for a lovely talk.